right, so this is problem number 11 on page 442. Basically, it says we got a spring mass system. Here's the statistics about what we got. We got mass of 0.5 kilogram, 8 newtons per meter spring, and the amplitude is 10 centimeters. It's going back and forth like this. And here's our setup. And we're asked these questions. What's the Vmax, Amax? What's the velocity at 6 centimeters? What's the acceleration at 6 centimeters? And then how long does it take it to go from, maybe let's just say this is the green stuff, to go from this location out to 8 centimeters. So just shy of the maximum amplitude. Okay, how long does it take to go from 0 out to here? All right. So this first part A, is going to go pretty quickly. And we have canned equations we can recall about these things. Before I do that, I'm just going to go ahead and do this little number. Omega is going to be equal to root K over M, and we're going to need this value. So it's going to be root 8 over 0.5. That's going to be like root 16, which is 4, and that's hertz. So that's a big deal right there to have. Okay, so for part A, we can just say, hey, this is our setup here. So for part A, we can say, hey, Vmax is equal to omega A. So we got 4 times 0.1, 0.4 meters per second. Okay, so we got 4 times 0.1. And then Amax is just going to be omega squared A. And that's going to be, what? 4 times 4 is 16, times 0.1 is 1.6. Okay, so that happened pretty quickly. And this is part A, so maybe we're kind of keep in mind, maybe they had us do this for some kind of reason to lead us into more complex questions. So let's just keep that in mind. I'm going to go ahead and put a bold box on this guy. Okay, for part B, they want to know the velocity at 6 centimeters. So you could do energy conservation to figure this out, and you could do some force stuff to figure out the acceleration here. But I think we're going to need the time eventually, and that we can't get that from energy and forces. So we're going to just go ahead, and I'm going to go ahead and figure out the differential equation for this. So I'm going to start setting that up. Okay, so I'm going to find the differential equation. So basically, I'm going to set this up. I know for my last question, I'm going to have to go from 0 to 0.8. So I'm going to go ahead and set up my differential equation to have the time 0 to be when it's moving to the right at the equilibrium position. I'm just kind of looking ahead a little bit here. So that's going to be at maximum kinetic energy. It's got to be at 0 displacement, but at maximum velocity, which we found right here. So we're going to actually grab something from that part A and recycle it. So I write out my equation for my velocity at time 0. So omega times time 0 is 0. And our initial velocity is going to be our maximum speed. To the right, plug in omega and amplitude. We see that that's 0.4 equals negative 0.4 sine phi, and when we divide that over, this is going to give us a -1 equals sine theta. That forces phi to equal negative pi over 2. So now I can write my differential equation. X as a function of time is equal to the amplitude 0.1 times cosine of omega t, so 4t minus my phi, which is negative pi over 2. Now I have a fully descriptive equation for anything I can talk about for this oscillating system. All right, and what are we supposed to do again here? So velocity at 6 centimeters and acceleration at 6 centimeters. Okay, so I'm going to figure out what time I'm at 6 centimeters, and then I can just feed that time back into my velocity and position and acceleration functions to find the values at 6 centimeters. Okay, so I took my position function, which is amplitude cosine omega t plus phi. I set the position equal to 6 centimeters. I solve for t, and I got this many seconds here. Okay, now I can use that time to figure out my velocity at that time and my acceleration at that time. So I'm going to go ahead and write those things out. Okay, so when I plug in my velocity equation for this time, that is the 6 centimeter time, I'm getting out of here. So we have negative omega a sine of the stuff here. And I get for the speed, the absolute value is going to be 0.32 meters per second. When I plug in this time into the acceleration equation, so that's negative omega squared a cosine of the phase stuff. With that time in there, I get negative 0.96 meters per second squared. All right, so now we can go. So we've gotten all of our part B stuff done there. Okay, so we just figured out what time it took to get to 6 centimeters and then plugged it into our velocity and acceleration equations. Let's go on to part C. So this is part maybe B right here. Kind of block that off. And now we can go to part C maybe here. Okay, so for part C, just to remind you again, we want to know the time it takes to go from our 0 position, which is where I set up my equation to have time 0 to be, out to 8 centimeters, directly to it. We know this thing's going to oscillate back and forth, so it's going to hit it once, then it's going to go out, and then it's going to hit it a second time, go back, and it's going to hit again. It's going to keep on hitting that, but we just want the very first time it hits there. So this is how I set it up. Here's my equation. I set the position equal to 8 centimeters and solve for t. And when I do this in my calculator, I get, well, I don't know, I'm kind of bumming on this, but so this is the position. The vertical axis is the position, and this is the time. And so 8 centimeters would be right here on this line right here, and that is boop, right around 0.232. Now my calculator is actually giving me this second one, and evidently I'm not smart enough to figure out why that is, but that's not the time we're looking for. We're looking for this first one right here. So 0.232 is, I think, right there is what we're looking at. So 0.232, it's at 8 centimeters. Okay? So it's going to be at 0.232 seconds. How long it takes to get there. Okay, I hope that was helpful. Thanks for watching.